market, a United Parcel Service. In this example, Federal Express currently runs their packages coast to coast by road. They use team-driven tractor-trailers. A team tractor-trailer is one where you have two drivers, and the two drivers, one sleeps and one drives, and then they rotate positions, and in this way they're allowed to legally drive continuously without stopping. They only need to stop for fuel, and they can go coast to coast without any rest breaks very quickly. But it's a very expensive way to travel. You have the cost of the general truck tariff, and then you have the higher wages that a team driver situation implies. Now UPS would like to move packages by ground, by rail, and they hope to do this because it would be cheaper, and they would like to be able to do it by rail in order to gain the speed advantage of a team driver situation without the expense of the truck carriage. Now they have run test trains in the past, in years ago, from Los Angeles to New York, and they have managed to do this in 65 hours. However, the host railroads have not decided to pursue this market, and one of the reasons they have not decided to pursue this market is the disruption to their host traffic flow. Their base traffic flow, they have found, is so terribly disrupted by these fast priority trains that the revenue gain is not worth the cost and disruption it causes to their other traffic. So there are two examples, current actual examples of this congestion and dispatching problem. So the objective of my research is to really quantify these outputs. I want to quantify capacity on a network, I want to quantify the value of service produced by a network, and I want to quantify the relative timekeeping of the services on the network. I want to derive pricing from optimal schedules. I want to determine an optimal schedule and then determine the pricing of services on that schedule. I want to know the marginal cost of a schedule change, and I would like to know the marginal cost of new services. And finally, I would like to really determine dispatch rules. I would like to have a set of best practices, kind of benchmarks or rules of thumb that can be used to train dispatchers so that in the absence of any kind of optimal intelligent computer doing all the dispatching, the people in the field can at least make educated decisions about how to best dispatch the trains. And I want to determine the relative cost and benefits of different dispatch strategies. There are a couple of predecessors in the literature that are directly related to what I am doing. I am primarily concerned with the literature of deterministic discrete time models, and the most relevant examples from this literature would be Brandland from 1998, who pursued a Lagrangian relaxation of a model similar to mine and a solution heuristic that determined feasible solutions. The one problem with his model was that the solutions still remained operationally infeasible. He would generate feasible solutions within the constraints of his formulation, but those schedules were still retained moves that were infeasible, operationally impossible in the field. The other literature to reference would be Caprara from 2002. Caprara, Italian railway network. One requirement of this formulation is the enumeration of what are called clique constraints, the enumeration of all possible interactions between different train paths. And unfortunately, this results in a constraint matrix that is exponential. It's exponential in the rows, and the problem size expands dramatically. It becomes very large, very fast, and it's not practical to apply to working problems. So my model, my formulation, is essentially a multi-commodity flow with a bit of a twist. We have a linear objective. We have a linear network constraints for each commodity, or essentially each train. And we have the side constraints. In my case, capacity is monitored at the nodes. But the twist is that we have to really be careful about opposing moves on the network, and I call these cells. And this is why I need to represent the model as pairs of flows, and I use a hypergraph formulation where the edges represent pairs of flows, and we'll see that in a minute. The linear objective consists of 4 train timing parameters for each coefficient. Each coefficient is a composite of 4 train timing parameters. The first parameter is the train utility, the value of the train completing its service. The second parameter is an early arrival incentive, a linear early arrival incentive. The third would be a stop cost, a charge for every time the train stops and waits. And the final parameter is a late departure incentive, and the real purpose of the late departure incentive is as an alternative to the stop cost. We could, for example, set both an early arrival incentive and a late departure incentive, and the two of those together act as a form of schedule compression that is somewhat of a substitute for the stop cost coefficient, and there are subtle dispatching scenarios where one is preferred over the other. Now, I mentioned a hypergraph earlier. I mentioned this business of pairs of flows, and here's a little diagram. We have a simple train arrangement on the left, and then we have a hypergraph on the right, a graph flow. And each of these edges, each of these arcs on the graph is representing the joint occupancy of two pieces of track over time. So, for example, the red arc in the middle there, it represents the occupancy of that track segment 2 for 2 time units, and it defines that the next track segment occupied will be track segment 3, and it will occur at time t+6. And it also shows that there are 2 other movements by the opposing train that could possibly be conflicted by this movement, by this track occupancy sequence, and those are marked by the blue dots. And those blue dots are cells, and cells are indicators of potential conflicts between opposing moves of trains, and this is important to model in a railroad situation. So here's the problem formulation. Very quickly, there's a linear objective at the top. That first constraint is a source node in the network. The next constraint is our origin, our first train move as a function of that source node. The next constraint is simply that flow conservation across the network. And then the next constraint is the sync, the flow sync node on the network. And finally, that last constraint represents the ability to link 2 trains into a continuous journey. So it's a funneling of the flow from the destination of the first train into the origin of the next train. Here are the side constraints, the complicating constraints. That first side constraint is the constraint on track capacity, and this final constraint are those cell constraints, those opposing move constraints that are so important in a railroad environment. Well, in spite of what I think are improvements in this formulation, we still have a very large problem. This is still something that is a real bear to tackle. Some of the reasons this problem formulation is so hard to solve is that there are many alternative solutions. We have a problem where there are many train paths that are not significantly different in their net value to the formulation, and these many alternative paths create a very large branch and bound tree that is very slow to fathom, because you have to crawl all the way down the branches of this branch and bound to find out whether or not that particular combination of variables is really an improvement over the current incumbent solution. So the blunt force approach to this problem is really it's futile. There is no way to simply throw computer hardware at this problem. We have a problem that is exponential in size, has an exponential branch and bound tree, and so doubling or tripling or quadrupling computer power doesn't even address the problem at all. So we really need an intelligent approach to this problem. What I have done is I have looked at this A matrix, this constraint matrix, and really found a very strong structure in this matrix. We can see what we have plotted here are the non-zeros in the A matrix. The blue areas are